Hello, this is Dr. Lukes, and this lesson is going to be for our Chemi 3140 class on molecular diffusion in liquids. So what we've seen so far is that we really can't expect that the diffusivity of A into B will be the same as the diffusivity of B into A, except in the case of equimolar counterdiffusion where the math does in fact work out that way. So we need to know the order of the AB subscript. Now in this, what this is saying is that this is the diffusivity of solute A going into solvent B. There's a limited table of values on page 431 that I've shown here and is, barely readable. But you can see this in your book. And they have things where we've got some things going as the solute here, mostly into water, but then we also can have things going the opposite direction. So water into ethanol, for instance, or ethanol into water. In general, you can expect kind of an order of magnitude difference. So for gases, our answers were all on the order of 10 to the minus fifth meters squared per second. For liquids, these are going to be on the order of 10 to the minus ninth meters squared per second. Now, if you do look at this table, you will see that the diffusivity is in meters squared per second times 10 to the ninth, meaning the diffusivity times 10 to the ninth is 1.64. So the diffusivity is 1.64 times 10 to the minus ninth. And then we'll also see very soon that for solids, we're going to go, orders of magnitude smaller, 10 to the minus 13th meters squared per second. Generally, the equation that we're going to most frequently use and that I'm recommending for this class is the Wilke-Chang equation. This is going to be the best for estimating liquid diffusivities. Like the one we were using for gases, it's going to have some kind of funny terms in here. So it's got this constant 1.173 times 10 to the minus 16th. I'm going to multiply that by the square root of phi times the molecular weight of B. Now remember, B is the solvent. Okay, so that's the bulk fluid that we have. Phi is going to be determined based on what that solvent is. So for water, it's 2.6. For methanol, it's 1.9. And for ethanol, it's 1.5. If it's not on this little limited list and you don't know anything better to use, then just call it 1. Temperature is going to be in Kelvin. We're going to divide that by the viscosity of the solvent. And the units on that need to be pascals per second or kilograms per meter per second. And then we're going to divide that by the V sub A to the 0.6 power. So V sub A is kind of an equivalent molar volume based on functional groups. And table 632 has the information you need. This is on page 433 of our textbook. And you can find these various values. So your oxygen, it depends on exactly how it's attached. Okay, so if it's in a methyl ester, it's 9.1, or a methyl ether, it's 9.9. And so you need to look at your molecular formula in terms of functional groups. Now there's one last little weirdness. If A, the solute, is water, you're going to, whatever answer you get, you're going to divide that by 2.3. Now, just like we did for gases, we will also be able to use this as a way to adjust for different temperatures. So maybe we looked in the table on the previous slide and saw that we had a temperature, was 273, and the actual temperature is 373. And so in that case, we can use this to put in a known diffusivity with a known temperature times a constant and solve this for what this constant is. Then that constant times the temperature we're interested in will give us the diffusivity we're interested in. Let's look at an example. So we want to estimate the diffusivity for liquid water into ethanol at 298 Kelvin, and we're going to compare this to the value that's on page 431. The data, so we've got A is our water, B is our ethanol, okay? From the H2O is going into the C2H5OH. Temperature is 298 Kelvin. The molecular weight of the solvent is 46.069. Since the solvent is ethanol, phi is 1.5, and its viscosity is 1.28 times 10 to the minus 3 kilograms per meter per second. Now, there is a data table in the appendix of our textbook that you can use, but you can also find this data all sorts of other places. And then that volume, molar volume for this is 18.8 times 10 to the minus 3. If I substitute that into the equation, I end up with this expression here, and then because A is water, I have to divide by 2.3. And so my final answer is 1.07 times 10 to the minus 9th meters squared per second. And if we compare this to the data table, we get 1.13 times 10 to the minus 9th meters squared per second. So the percent difference is incredibly small, and this formula does seem to be a fairly good model. So this concludes this lesson. In the next lesson, we're going to look at electrolytes and biological liquid systems. Thank you very much.